This talk is called Effective Java 3rd edition, Keeping It Effective, and the talk is all about the new edition of my book, which is now available at Amazon or your favorite brick and mortar bookstore if you can still find one. The book has one new chapter. It's got 14 new items. 2 of the old items were retired because they were no longer interesting. And every single existing item was thoroughly revised. Every piece of code in the book was revised to use new idioms and new constructs. Here's how Java has kind of evolved from when the first edition was released. The first edition was in 2001. The book was 232 pages, and it covered the language as it existed at the time, Java 4, which was kind of the original language plus anonymous classes, asserts, a few other things. The second edition was released 7 years later in 2008, and the book grew to 315 pages because the language had grown, principally in Java 5, but a little bit in Java 6. It got generics, enums for each autoboxing, var args, and so forth, the concurrency utils. And that edition served us well for almost another decade, but it was getting kind of moldy about the time that lambdas and streams were added to the language in Java 9. So the third edition covers lambdas, streams, optionals, the default methods that were added to interfaces, try with resources, which was added in Java 7, and modules. That's a lot of stuff. I always wanted Effective Java to be a little book, and it used to be a little book, but when you have a big language, you can't write a little book. So it's grown to be a bigger book. Of course, I cannot cover all of the new stuff in this talk, so I'm restricting the coverage to lambdas and streams, and I can't even cover all of that. If you look at these 5 topics I'm going to be covering today, you'll see each one has a number after it, and that number is the item corresponding to the material. I hope to make it through all 5, but if I can't, I'll cut the 5th one, and that means I'll move fast, but I'll try not to lose anyone. First thing I'm going to talk about is why you should prefer lambdas to anonymous classes, and I wasn't kidding when I said I'm going to go from board to board. All right, so historically you used anonymous interclass instance creation expressions for your function objects. So if you needed to, let's say, sort a collection of words according to string length rather than alphabetical order, you would have to pass in a comparator which took 2 strings and returned a negative number, 0, or a positive number, as the first one was shorter than, same length, or longer than the first. And this was the best way to do it. You would basically create a new comparator of string whose compare method took 2 strings and returned integer.compare of s1 length, s2 length. And that was great as far as it went. It was adequate for the classic object-oriented design patterns that we learned in the Gang of 4 book, such as strategy and command. But you couldn't do everything with it. And now there's a better way. Now you can use lambdas. And here's a new piece of code that does exactly the same thing. We say collections.sort of words, and this time, instead of passing in that anonymous class instance, we just have a lambda. It takes 2 strings and returns the result of calling the compare method on the 2 strings. That's great, but we can do better. At the same time as they added that, they added comparator construction methods. And this, by the way, assumes that we've done a static import, so I can, which I advise you all to do. There's no question as to what I'm talking about, and it reads much better. So now, instead of explicitly passing in a lambda, you can just say comparing int of string length, which means gives me a comparator that compares the int that I get by invoking the length method from string on the given strings. So, that's even nicer, and moreover, these comparator construction methods do something wonderful for you. They guarantee that the comparators that you get will actually obey the comparator construct, which is a fairly complicated contract. So you should pretty much always use these comparator construction methods when you can. But wait, there's more. You can do even better than that. They also added, using these interface default methods, they added a sort method to the list interface. So you can simply say words.sort, comparing int of string length. And the lovely thing about this is it reads like English now. Sort the words, comparing the int that is the length of the strings. Isn't that marvelous? So that's what you should do now that you can. It looks beautiful, but how does it work? There's a lot of magic to make all of this work. And under the hood, the way it works is type inference. So when the program says, hey, sort words, and you pass in this lambda, S1, S2 returns integer.compare of S1's length with S2's length, what's really going on is, there's a type cast to comparator of string. You have to tell it, make me an object of type comparator of string, and you have to tell it that these arguments, S1 and S2, are in fact strings, but the compiler figures it all out for you. How does it do it? It does it using type inference. And how does type inference work? The best way to think about type inference is that type inference is magic. It's like too complicated, really, seriously. The point is, the rules to type inference are so complicated, they take up a whole chapter in the Java language specification, and it is a very complex, very technical, very mathematical chapter. It's in excess of 60 pages. Just out of curiosity, and don't be embarrassed, how many people have actually read that chapter in its entirety? So in this audience, one, and that's about what I expected, and I'll bet you're like a compiler engineer or something like that. Okay, really confused. Did it help solve your confusion at all? Good, good. So basically the people who, it was designed for the people who have to implement compilers that actually have to do the type inference. It's extraordinarily complex, and no one knows how it works, and that's okay. The right way to deal with this is just assume the compiler will be able to figure it out. Write down the lambda that you want, and if the compiler can't figure it out, it will bitch at you. It will give you an error message and tell you why it couldn't figure it out, and you'll say, okay, I gotta add a little bit of type information here. You add the type information, and then you're good to go again. So that's the way you should deal with the magic of type inference. Here's a caveat regarding type inference. In order for type inference to actually work, it needs the generic information. So in the previous edition of this book, I told you, hey, never use raw types. Don't say list, say list of string, because if you just say list, you lose all the benefits of generics. You won't get compile time type checking, you won't get type safety, your program can blow up at runtime, it can compute wrong results. But now it's even worse. The third edition says it even more strongly. It says, hey, if you use raw types, you won't be able to use lambdas because they won't be able to infer the types, and the lambdas just won't compile. So at this point, the usage of raw types should be considered strictly verboten. The rule for when to use raw types is don't. The implication of that, the summary, is that you have to understand generics in order to use lambdas. You simply can't use lambdas without generics. So do you guys remember this old chestnut, this old program? Here, this is a long section, so I'll share my time with the people on this side of the room. So you guys, by any chance, remember this program, which is in the previous editions of Effective Java, which basically is an enumerated type representing an arithmetic operation, either plus, minus, times, or divided by, and it has like an abstract method out in the enum, and then constant specific class bodies, where each enum constant provides its own implementation of the apply method in order to do the correct thing, so that the plus constant does addition, the minus constant subtraction, times multiplication, and divide does division. You guys remember that? Show of hands. I just have curiosity. Well, a bunch of you. But anyway, so if you could give different behavior to each enum constant by having the constant override an abstract method that was declared in the enum itself. And I thought this was pretty cool. I liked it. But it turns out you can do way better now. In that book, I also said that you should prefer sort of constant specific data to constant specific class bodies. This is a sledgehammer. This is a power tool. Well, I think I mixed my metaphors. This is a chainsaw. This is a power tool, and you shouldn't use a power tool when a hand tool is called for. Ideally, you would just pass in a piece of data to describe the different behavior, and now you can easily do it. Here's how the code looks. See, now, instead of simply passing in the symbol so that it prints out properly, I pass in the symbol and the operation. And the operation here is just a lambda. So for plus, I pass in given x and y, return the sum of x and y. X comma y goes to x plus y, and similarly for all the four others. So now I don't need to have any abstract methods in the outer class that is in the enum itself. Instead, I simply have an apply method, has the same signature as the previous one did, and it returns op.apply as double x comma y. And what is that really doing? Well, if you look at the type of op, you will see it is a double binary operator. And that is one of the standard functional types provided by Java. You know, in order to make these lambdas work in a language that doesn't provide sort of functional types at the language level, like a type representing, you know, a method that takes 2 ints and returns a double. Since the language doesn't have that, they just provided a whole bunch of types, we'll discuss them later, which are the standard functional types. And in this case, the one that perfectly does what we need is double binary operator, which is an operator that takes 2 doubles and returns a double. And this simply takes a double, you know, so this guy is a double binary operator. That is all of 4 of the lambdas that are passed in. And you can apply it simply by calling apply as double, and we're done. So now there's a much nicer way to do what we used to have to do in a sort of a nasty way. So I've said, you know, lambdas are great. Use them instead of anonymous classes. When shouldn't you use lambdas? Well, lambdas lack names and they lack documentation, right? When you have a lambda, all you see is a gob of code in the middle of your code. That's fine if your lambda is self-explanatory, if it's short and sweet. So if it fits on a line, great, but they should rarely exceed a few lines, because if you have a bunch of code, you know, being passed in, and you look at it and you can't figure out what it does, then you can't figure out what the code, including it, does either, and you're in bad shape. If a language would be too long or complex, there's an easy way out. You should all know this trick. Extract the lambda to a separate named method, and then use a method reference to that method instead of a lambda. And once you have a named method, you can name its parameters, you can give its parameters types, you can, you know, describe the semantics of the method, you can put comments inside the method, and it's not like you've blown up the code by putting all this stuff in line. So lambdas are good only when you're actually passing a small amount of code. And lambdas haven't completely killed anonymous classes. There are still a couple uses for them. First of all, lambdas require a functional interface, which is basically an interface that has a single abstract method. One interface, one abstract method. What if you have an interface with 2 abstract methods? You know, and there are some like that. You can't describe that with a lambda, so you'll need to use an anonymous class instance. Or what if you have something that isn't an interface? What if you have something like timer task that is an abstract class? You can't create an instance of an abstract class with a lambda. So those are times when you'll still need anonymous classes. And finally, and this is a tricky one, but it's very, very important, lambdas cannot access themselves. If you say this from inside a lambda, what does it refer to? Yell it out if you know. Come on, you guys know. You're just bashful. Enclosing instance, absolutely. So the point is, it doesn't refer to the lambda itself. It refers to the instance in which the lambda occurs. And that's usually what you want, but it isn't always what you want. And in the case, for example, of a callback, suppose you're registering a callback, and that callback needs to eventually remove itself, needs to deregister itself. It needs to talk about itself. It needs the this pointer, and a lambda can't get the this pointer to itself. So you simply can't use a lambda there. That's another case where you have to use an anonymous class instance or do other gymnastics. All right, next section is, no, I'm going to stay here for the beginning of this section. Oh, is there a screen over there too? Sorry, cameraman. Fairness to audiences. All right, so, right, you should also prefer method references to lambdas. Lambda, generally speaking, but not always, lambdas are succinct, right? Lambdas are these nice little things, but so here's an example where, you know, I'm taking a map and I'm making a frequency table. This one line, it's kind of an amazing thing, makes a frequency, well, you have to do it repeatedly to make a frequency table. But anyway, the thing is that what I'm doing here is I have a lambda inside, and because I'm short on time, I won't discuss the details of this, but I have a lambda that takes 2 variables called count and increment, increment in this case being 1, and returns count plus increment, so it adds 1 to count. That's nice, but how about just saying integer sum? I'm just saying the sum method on the integer class, which is a pre-existing method that takes 2 capital I integers and returns the capital I integer that is their sum, right? So that's you know, even easier, or even easier to read and even shorter. And the more parameters you have, the bigger a win it is to use a method reference instead of a lambda. And the reason that is that basically the lambda actually has to list each parameter explicitly, whereas the method reference lists none of them. So if you've got 8 parameters, a method reference is a lot shorter than a lambda. But if you do use a lambda, you do get another opportunity to do documentation. In this case, we have the count, the previous count associated with this key, and the increment, the amount to be added to that count. There's no such documentation here. So sometimes you're better off using the lambda because you get the opportunity to name these parameters. But if you do use the lambda, name the parameters carefully because it's a wasted opportunity for documentation if you don't. Hello. Wouldn't that be terrible if this didn't work for you? Okay, so occasionally lambdas are even more succinct. It is not always the case that the method references are succinct. So for example, suppose you have a short method name in a long class name. It's a lot easier to just say, hey, take no arguments and call action than it is to pass a method reference to, gosh, this class name is humongous, : action. And moreover, I would argue that the lambda is also more self-explanatory because it makes clear that action is in scope at the point of invocation, right? That action is defined in this class. Whereas if you forget that the class name is, gosh, this class name is humongous, then if you use that method reference, it could be referring to something elsewhere. So, the bottom line is there are no hard and fast rules for when to use a lambda and when to use a method reference. You should use whichever one is shorter and clearer. Lambdas can be function factories as well. I would run out of time if I discussed this one, but there are, the language provides a function factory called function.identity that returns the identity function. And it turns out you're better off typically just saying a lambda that takes x and gives x, because it's absolutely clear what this means, whereas people might not know about this. When you have a method reference or a function factory, the documentation is elsewhere and you have to go chase it down. All right, now, there are 5 kinds of method references. Most people only use one of the 5. Well, not one of the 5, but they don't know all of them. It's really important to know all of them. All of them are useful. So one of them is a static method reference, which is just a reference to a static method, like integer : parseInt is the parseInt method on an integer. You can do a bound method reference. Those turn out to be extraordinarily useful. And with a bound method reference, what you can do is you can provide an object on which the method reference will always be invoked. So in this case, the example here, I use a bound method reference to kind of capture the value returned by instant.now, and in one really short expression, I have a method reference that returns true if a given time is after the time at which the bound method reference was evaluated. So these things are pretty powerful. I'm a big fan of bound method references. Unbound method references basically take an instance method, but add the instance as an additional parameter to that lambda. So you've got one more sort of artificial parameter that isn't in the method declaration. And then class and array constructors both have method references, and those are very useful as object factories. If you need to pass in a factory to something, just pass in a pointer to, or I should say a reference to, a constructor, and you can also pass in array constructors. So like int : new is something that takes a single value, which is the length of the array to be constructed, a single int value, and returns an int array of that length. So that's all the different kinds of method references. Know them and use them all. So the bottom line is that almost anything you can do with a lambda, you can do with a method reference, and vice versa. So you should always use whichever one is clearer and more succinct. Typically, that's method references, but not always. So use your best judgment. And the best part of this all is you can change your mind later. And the reason you can change your mind later is this is just an implementation detail. This does not affect the API one way or another. All right, so next section is called Favor Standard Functional Interfaces. Because, as I mentioned before, the language provides a whole bunch of these new standard functional interfaces. I gave an example before of the one that took 2 doubles and returns a double. So let me give you an example where you might want to use one. Before lambdas, the template method pattern was common. A template method pattern is, who knows the gang of 4 template method pattern? Raise your hands. Well, some of you, but not all of you. So the idea basically is that you had a class which you kind of specialized by overriding an abstract method, or a method that was, did nothing and acted like an abstract method. So an example of a template method pattern would be the linked hash map class, where you can override a method called remove eldest entry, and that method is called every time you insert something into the map with the newest thing, sorry, not newest thing, with the oldest entry as a parameter, and it gets a chance to decide whether to kick it out of the map or not, whether to evict it. And this lets you write caches easily. Like for instance, if you override the method with something that just returns current map size is greater than some maximum size, 57, then you have a cache, an LRU cache, that just keeps the last 57 entries that were added to the map. So that is the template method pattern in action. But now you're better off using the strategy pattern. You can basically, instead of extending a class and overriding a method, you simply pass the method into the constructor as a little bit of behavior. So in this case, it's that eviction method, the remove eldest entry method, becomes, instead of an abstract method on a superclass, it's a parameter to a constructor. This isn't actually in Java now. This is kind of pretend, the way it would be if we were writing the class now. You could have a linked hash map constructor that took an eldest entry removal function, which is a function that gets the eldest entry and returns true if you should kick it out, false if you should leave it in. And as defined here, I've actually defined an interface for this eldest entry removal function, where it has a single method called remove that takes a map from K to V and a map entry from K to V. That's an unnecessary functional interface. It's ugly. You don't need to define this interface. You should use one of the standard functional interfaces instead. Which one should you use? Well, let's see. The one that you should use is, I forget, and I'm going to move on because time. This is a shorter version of this talk than I've given before. But anyway, so Java has 43 standard functional interfaces, which is quite a few. It's like, here they are on the slides, pretty scary, right? How can you possibly remember all of these things? Well, it's hard. You can't really remember them per se, but luckily there's a lot of structure to these 43 things. You can see that I've bold-faced a few of them. A consumer of T is something that takes a T and gives back nothing. It eats T's. So for example, you pass one of those as the body of a loop, and you just apply the loop body to each of the T's. It sort of consumes them all. Function from T to R is a function that takes a T, returns an R. Predicate of T is something that takes a T and returns true or false. Supplier of T is something that takes nothing and returns T's. And if you remember all of these, you can actually, and finally, a unary operator of T is something that takes a T and returns another T. So for example, let's say unary operators on an integer would be like negate or absolute value or something like that. Okay, so basically the idea is if you only remember the boldface ones and you learn the structure, then you can figure out all of the others when you need them. And in my book, in the corresponding essay to this, I basically describe the structure well enough that I think that if you read it a couple times, you'll always be able to come up with the other one when you need it, unless you're giving a talk. Yeah, so there are the 6 basic ones written out, and we've got sort of examples of each. So string.to lowercase is a unary operator, turns a string into its lowercase equivalent. Big integer of add is a binary operator. It takes 2 big integers and returns their sum. Collection is empty is a predicate. It takes a collection, returns true if and only if the collection is empty. Arrays.asList is a function from T to R that basically takes an array of T and returns a list of T. And let's see, instant call now is a supplier, I guess, of date time. Just returns you call with no arguments and it returns the current time. And finally, system.out.println is a consumer of T. It takes an arbitrary T and it prints it out. It eats it and does, prints it. So there you go. So what are the advantages? Why should you use these standard functional interfaces? Well, not just because I say so. First of all, it makes your APIs easier to learn by reducing the conceptual surface area. You don't have to learn all of these new little, adjunct types in order to use the enclosing type, because it's taking advantage of the knowledge that you already have. Also, it provides many interoperability benefits. These functional types aren't just kind of, random things. Some of them provide methods to combine, to do other interesting things with other elements of themselves. So, a good example is predicate is great, because predicate has one method that takes another predicate and returns the predicate that is the and, another one that returns something that is the or of the two predicates, and then there's one that returns not of the given predicate. And given that you can do those, by stacking them up, you can get arbitrary Boolean compounds of existing predicates to form new predicates. So that's a pretty powerful thing. In our linked hash map example, there we go. I don't know why I put this all the way over here, but anyway, remember I said it was coming up. A bi-predicate, that is binary predicate, a predicate that takes two arguments, whose first type is a map from K to V, and whose second type is a map entry from K to V, should be used in place of our eldest entry removal function, which was a straw man. I told you when I put it in there that you really didn't need it and shouldn't have it. When shouldn't you use a standard functional interface? It turns out that there are absolutely times when it's wrong to use them. Well, you can't use one when none of the standard interfaces apply. There are only 43 of them, and 43 is not infinite. If you've got 3 or more arguments, or it just doesn't fit into any of those patterns, then you have to make your own interface. But sometimes there are cases where an existing standard functional interface could be used, and yet you shouldn't use it. Let's consider the case of comparator of T. It is structurally identical to an 2int bi, that is binary function, of TT. But it seems clear that it would have been wrong if the Java APIs said 2int bi function of TT everywhere where they say comparator. That can't be right, can it? No. Why not? Well, several reasons. Comparator is used all over the place, and every time you see comparator, you know, aha, he's passing a sort order on two things. The name, is short and sweet and provides useful information. Also, there are very strong requirements on what constitutes a valid comparator. Not every, 2int bi function is a comparator. In order to be a comparator, it has to be a total ordering on its arguments, which means it has to, obey certain algebraic constraints, and that is the general contract of comparator. You can look it up in the specs. And by implementing comparator, you are saying, you are guaranteeing to the system that you are actually obeying all of these constraints. And an interface lets you do that. That is a special purpose, new interface, lets you do that. You can sort of, for each of the methods in the interface, which is only one in the case of a functional interface, you can basically give a contract of what that method is required to do, just as the comparator interface does. Also, you can put useful default methods on your own interfaces. So comparators, just like predicates, have all sorts of useful operations, and they have these static methods, the comparator construction methods that I told you about afterwards. So you can basically load up your interface with power tools when you're writing your own interface, which don't exist necessarily on these standard functional interfaces. So, this basically gives you a recipe for figuring out when you should write your own functional interface. An interface should have one or more of these characteristics that comparator has. It should be commonly used. It should have a good descriptive name. It should have a strong contract associated with valid instances of it. And it could benefit from the existence of default methods or static methods. If a number of those 4 things are true, such that on balance you think it deserves its own interface, then write your own interface, even if there's a pre-existing standard functional interface. But if you choose to do that, it is incredibly important that you remember this. A standard function, a functional interface is an interface, and you have to design all your interfaces very, very carefully. Interfaces are the most fragile things in your whole design. If you get an interface wrong, it's like all of the pre-existing implementations of that interface, everything kind of has to live with it pretty much forever. even though we now have the ability to add methods to interfaces using defaults, if you make a mistake in defining an interface, your life will become a living hell. So if you're designing your own functional interface, make sure you get it right. All right, so the fourth of 5 sections, and I should check out when my stopping time is here. I've been at it for 30 minutes. I think we'll be okay. All right, so use streams judiciously. So a quick review. How many people here are sort of experienced stream programmers? So a lot, but not everyone. I will go over this slide, but I'll do it quickly. So what is this? What is a stream? It's basically just a whole bunch of data objects from a collection or an array or some sort of input device in sequence. It doesn't say where they come from, but it's like a whole bunch of objects in sequence for bulk data processing. And you do that bulk data processing using what is called a stream pipeline. A pipeline has 3 things. It has exactly one stream generator, that is a data source that somehow returns a stream over a given type. There are a bunch of instances of a type. And then you have 0 or more intermediate stream operations. The intermediate stream operations take a stream of one type and return a stream of either the same type or another type. So they basically do some transformation on the stream. They negate all the objects, or they take the sums of the prefixes, they just do something to the data. You can repeatedly do stuff to data. In business context, they typically think about, whatever, like if they're customer accounts, you might get the amount that they're in arrears, and if it's more than a certain amount, you generate, some sort of, well, the generate is the last part. There's one final operation at the end of the stream. After you do all these intermediate transformations, then you take the results of the transformation, which is still a stream of T, and you consume it. You do something with it, and typically you turn it into something else. So you might just print it out, as in turn it into, some text on a screen or in a GUI, or you could turn it into a collection. There are things called collectors, which are a standard set of terminal stream operations which turn streams into appropriate collections. And this supports what they call mostly functional data processing. It's kind of like functional programming, except not necessarily all the way there. It also enables painless parallelism. You can just say .parallel on your stream, and all of a sudden, as if by wizardry, the stream executes in parallel. And you may or may not see a performance improvement. More on that in section 5. So here's a little example. Suppose you want to compute the first 20 Mersenne primes. To review, for people who aren't math majors, a Mersenne number is a number of the form 2 to the p plus 1, a power of 2, minus 1. A power of 2 minus 1 is a Mersenne number. And if the exponent p is a prime, some of these Mersenne numbers are in fact primes, and those are called Mersenne primes. So 2 to the 0 is 1, minus 1 is 0. That's not a Mersenne prime. But 2 to the 1 is 2, well, let's do 2 squared is 4, minus 1 is 3, which is prime. 2 cubed is 8, minus 1 is 7, which is prime. So, 3 and 7 are Mersenne primes. And it turns out that there are a bunch of Mersenne primes which got mathematicians very excited, back in the 1500s. But then they realized that not all these Mersenne numbers were primes, and anyway, it's still interesting from a number theoretic perspective. So suppose, as I said, that we want to print the first 20. It turns out that it's very easy to do that using streams. So here's how we're going to do it. First, we're going to write a method that returns a stream of all the primes. Whoa, you may say, a stream of all the primes. How can you do that? That's infinitely long. Well, it is, but the lovely thing about streams is they're evaluated lazily, right? You pull data out of a stream. Every time you need another item from it, you say, give me the next item. This happens under the covers. This is done by the stream processing library. And so that means it's perfectly okay to have a stream whose length is infinite. So in this case, this simple little one-line function here called primes actually returns a stream of all the primes. And how does it look? It returns stream.iterate, that is a static factory method in stream that generates a stream. And the first thing you pass in is the initial value of the stream. So the first thing we're returning is big integer.2. I'm assuming we've statically imported all the big integer stuff because it makes these examples fit on a slide. So the first thing we return is 2, and the next one we return is the result of applying big integer.next probable prime to the previous thing. So if you call next probable prime on 2, you get 3. If you call it on 3, you get 5. On 5, you get 7. On 7, you get, I guess, 11, and so forth. Basically, this just is a stream that runs through all of the primes. But we don't want all the primes, we want all the Mersenne primes. So how do I convert this stream into a stream of the Mersenne primes? Well, first I map each of the primes to 2 to the value, 2 to that power, and I subtract 1, right? So that gets me the Mersenne number, not Mersenne prime, but Mersenne number corresponding to that prime. And then I filter the Mersenne numbers using Mersenne.isProbablePrime of 50. I apologize for 50, I apologize twice. First, I apologize because it's a magic number in this program. Magic numbers are bad, but the real apology is I wrote this API and you never should have had to pass it in the first place. You know, so double my bad. But anyway, this thing here is just a predicate that returns true if the thing that's passed in is probably prime, where probably in this case means certainly. It'll return true if it's prime, otherwise it'll return false. And then .limit 20 just says, and give me only the first 20 elements on this stream. Once you hit 20, stop, right? So if you look at this thing, the stream generator here is the invocation of primes, and then I have an intermediate operation to map them to the Mersenne numbers, another intermediate operation to filter the Mersenne numbers to Mersenne primes, another intermediate operation to throw away everything after the 20th, and then finally I have a terminal operation, which is the for each operation that simply applies a consumer to every element of the stream. And in this case, the elements are the Mersenne primes, and the consumer that I apply is system.out.println. So this little 4-line program does in fact print the first 20 Mersenne primes. Great, right? So there's your introduction to streams. And let's see. Here, now that's part of, I'm wondering about time. How much time do I have left? I'm gonna go check. 13 minutes, all right. So I'm gonna rush a little over this section because I want you to enjoy the final section because it's fun. But anyway, so here's an iterative approach to computing all the anagram groups in a dictionary. You know what an anagram is? When 2 words are the same letters in a different order, like stop and pots and opts. So if you want to compute all the anagram groups in a dictionary, the best way to do it is to make a map which maps every word's alphagram. You alphabetize the letters in the word, and you map the alphagram to a set of all the words sharing an alphagram. So for example, you know, TOPS, let's alphabetize those. That's OPST, obst. All of those things, all of the anagrams have the same alphagram. That is, if I alphabetize any of these things, it basically permutes the letter into the same order, which is alphabetical order, right? So if you look at this program, what does it do? You know, I get I have a file, it's called dictionary, a minimum group size that I'm interested in, and then a map from the alphagram to the set of strings that are the anagrams of that alphagram. Then I make a scanner over the dictionary. Notice that I'm doing it using one of these try with resources. Try with resources is great. You should always use it, but I'm not talking about it today. And then while there's anything left in the scanner, so I'm reading all the words in the dictionary one at a time, I get the next word out of the dictionary, and I call compute if absent. This is a new method, and it's wonderful. It basically looks something up in the map and either returns what it found. So if there's already an anagram group for that alphagram, it just returns it, or it invokes a method that's passed in, typically a lambda, and returns that. So in this case, if there's already, you know, we alphabetize the word, look it up, and if there's already a set, we simply return that set. And otherwise, there was no set, so we return a new tree set, right? So either way, we get a set, and then we simply add the word to that set. So we basically accumulate all the words in the dictionary into the appropriate sets of anagrams. And then when we're all done, we iterate over all of these anagram groups. And if the size of a group, what's the minimum group size that we'll ever see in here, by the way? 1, exactly. If something has no anagrams, we'll see 1. But anyway, if it's big enough, if it's bigger than min group size, which was passed in to the command line of this program, then we print it out, both the group size and the group. That's it. So it's kind of neat, right? I love this about the collections API, that this program, which takes up like a whole chapter in the STL guide, is one slide using collections. And here's the helper function to alphabetize a word. It's totally straightforward. You dump the string into a char array, sort it using arrays.sort, and then you return a new string whose characters are those characters. And that's it. That'll actually run. So suppose you want to do it all with streams and lambdas. How does it look? It looks like this. It looks incredibly ugly. It's unreadable. And because I'm rushing, we're not even going to look at it at all. I'll just say you don't want to do it this way. This is an example of streams gone crazy. This is an example of something that's too streamy for its own good. And so what do? Does that mean you should do it the old way? The answer is no. There's a happy medium. Here it is. Look at this nice short little program. Let's actually go over it a line at a time, and because I want to finish in the middle, I'm going to do that over here. Sorry, guys. First line, we say, hey, get the file path that is described by the first argument. So the argument will be like, slash whatever, my dictionary. Anyway, then get the minimum group size from the second argument, and then try on a stream, which we get by calling files.lines of dictionary. So files.lines is a wonderful thing that you should all know about. It basically returns a stream of strings, which are all of the lines in the given file. Ain't that great? It's much easier to process files with streams than it was before. And then for each of the words, we collect the word, grouping it by the function that we get by alphabetizing the word. So in essence, you alphabetize the word and you collect it, and that actually gives you the stream that you want. I mean, you're done. That line, after you do that, you already have a stream from, which is basically, you don't have a stream, you have a collection, which maps you from the alphagram to the anagram group. And then we call dot values. So that gives us, I've thrown away the alphabetized words because I don't need those. All I need are the groups. So now I have basically a collection of groups, and then I make another stream out of that, right? So I went from stream to collection back to stream. This is a stream of the anagram groups, and I filter based on the group size. If the group size is greater than the minimum, I let it pass, otherwise I don't. And finally, I call for each. For all of the ones that are sufficiently large, I invoke this method, which basically prints out the group's size and the group. So that's it. Now it takes only half a slide, what used to take a full slide, and I think it's pretty gorgeous. Notice, by the way, that I'm still calling alphabetize of word. Why am I doing that? Well, the reason is that streams don't offer direct support for chars. It would be really ugly and confusing if I tried to do this using streams. I do in that first ugly example, and you can go back to it in the slides if you want to see how it looks. But don't do it. It's more difficult to read, it's more difficult to write, and it's probably slower. If you don't believe that you shouldn't use streams on characters, I got a little puzzler for you. Here it is. So I have a program here. It has the string hello world, and then it calls .chars, which returns a stream of the chars in the word, the string. And then for each of these chars, I call system.out.print. So what do you guys think it prints? ASCII characters. Which ASCII characters? Hello world. This program looks for all the world like it should print out hello world. But what does it actually print out? This garbage. Why does it print out this garbage? Because of chars. This thing called chars on a string actually returns a stream of int, because there is no such thing as a stream of char. The library would have been too big and too complicated if they had had streams on every primitive type. So they just picked the most important ones, which are ints and doubles and longs, and you have streams of those. And if you're not one of those, well, sorry, use the best major type. And if you want it to actually print out the right thing, then what you have to do is you have to cast that int back to a char before you do the print. So this version actually prints hello world. So the moral here is that strings are really only for int, long, and double. The rest of the primitives are missing, so just don't use your streams for string processing. So here's a conundrum, and this one I want to do really quickly. But we have two different methods, each of which return like all of the elements from group A map, so cross product with the element from group B. So basically, suppose I want every possible card in a deck. I can just iterate over all the suits, iterate over all the ranks, and then add to the resulting deck a new card of suit, rank. You've all seen that before, right? That's a standard nested loop. Below it, I have the stream equivalent, where I get a stream of the suit values and then I flat map it using a mapping from the suit to a stream of the rank values, and then I map that to a mapping from the rank to a new card of suit, comma, rank. So we have a nested lambda here. We have the flat map construct here. In fact, it's a doubly nested lambda. What we're doing is something called currying, if you're into functional programming. So my question for you guys is, which one of these two things is better? Which is the better way to get a deck of cards, to get a cross product of a Cartesian product of two sets? Do you prefer the iterative one? Yeah, so we got maybe a third of you. Do you prefer the streamy one? Oh God, just a few of you. So most of you aren't answering. Anyway, I do not think either of the answers is necessarily correct. I think it depends on who you're working with. If you're like hardcore functional programmers, by all means use the second one. You know, if you come from a more procedural universe, use the first one. Without a doubt, everyone can understand the first one. You know, the second one may be a little bit shorter and it may be more comfortable for you. There's no correct answer here. Do what feels right. All right, so the bottom line is streams are great for many things, but they're not a panacea. When you first learn, you might want to convert everything to streams, but don't do it. It may make your code shorter, but it sure as hell won't make it clearer. So exercise good judgment. Properly used, streams can make your programs both shorter and clearer. Most programs of any length will combine iteration and streaming. You still need both of them, and you need the judgment to know when to use which. And if you buy my book, I'll teach you as best I can. It's not always clear at the outset which to use, so often what you have to do is just code it up and see which works better. All right, one last very short section. So you remember that Mersenne Prime program that I showed you one section back? When I run it on my quad-core desktop machine, it runs in 12.5 seconds. That's pretty good, right? You know, because it's 20 Mersenne Primes, and they get pretty darn long by the time you get to the 20th one. 12.5 seconds. Let's suppose I run it in parallel. I just add dot parallel. How long do you think it will take to run? 60 seconds. So you think it'll be longer by a factor of 5. Could be the same time, though. How many people think about the same time? So about the same time, maybe half of you. How many people think shorter, that you'll actually buy you something? Maybe an eighth of you. All right, so here's what it does. It turns out that it runs very, very slowly. After half an hour, I gave up, and my room was considerably hotter. Like all 4 cores, 8 hyperthreads of my machine had been pumping away for half an hour, and it blew a lot of hot air into my room, but it didn't print out anything. So what happened? Why did it run so slowly? It turns out that the streams library has no idea how to parallelize that program, and all of the heuristics fail miserably. Even in the best case, it turns out that a stream, the dot parallel isn't likely to run well over a stream that you got using stream.iterate, or if you use limit. And this one does both. It uses iterate to get the thing, and then limit to say, oh, I only need the first 20. And this absolutely isn't the best case. This is the coup de grace. The thing about, you know, like calculating Mersenne primes is that each one takes as long as the sum of all the previous ones to calculate, right? So basically calculating one more doubles the runtime. And it turns out that the ordinary heuristics say, well, we don't know how many to calculate, so we'll just calculate a bunch and, you know, then we'll trim it down to what we needed. If you calculate even one more, you've doubled the time. So you're just dead. And the moral here is do not use dot parallel indiscriminately. Only use it if you have reason to believe it will make your program run faster. When does it work well? Well, it works well. Do I have like 2 more minutes or 1 more minute or something, timekeeper? 1 minute. Okay, so it works well if the set is predictably stream is predictably splittable, and if you use an appropriate terminal operation. And you know, the happy ending to this story is here's something to calculate pi of n, the number of primes less than n, takes 31 seconds on my machine. If I parallelize it, it runs in 9.2 seconds, which is 3.7 times as fast on a 4-processor machine. So I'm basically getting linear speed up. So if you use parallel appropriately, and that is very, very, very rarely, then it can actually make things fast. But parallel is very dangerous. It's merely an optimization. Don't use it unless you think it's going to help. All right, in conclusion, Java is now larger and more complex than it ever was before. That's a bad thing. It is now a multi-paradigm language, in the words of Bjarne Stroustrup. And now you have to know not just how to use the features, but which of the competing features to use. Lambdas and streams can be a big win, but only if you use them judiciously. With great power comes great responsibility. Here's the book. If you want to buy it, if you use this code, Bloch 991, you'll save 35% at informate.com. It should say, yeah. But also check out Amazon, because I think that might be cheaper. If you got questions, ask me outside. Thank you very much.